recording just now. Okay. So does anyone have any questions, anything to do with the module from what we did last week at all? Anyone want me to go over anything at all? Can everyone hear me okay? Yeah, just say yes.
Yes.
Oh, good.
Yep.
Yeah. That's great. Right. So if you've got questions, then just ask, and I'll try and answer. So what I'm going to do is I'm going to go over public key encryption as we did today, probably a bit quicker than I did this morning. I don't have a Mentimeter test for you this week, unfortunately, so I apologise for that. Next week, I think it's Bruce Snyer next week for our evening session. So it'll be 1 o'clock New York time and 6 o'clock our time. So I'll start that session a little bit earlier than this week. Right, so if it's okay, I'll go over public key encryption that we went today, and I appreciate you might have been part of the lecture today. If there was something that didn't quite go in, or if you've got questions about anything like that, then just say. So I'm just going to get my presentation ready. And that should be good to go in a minute. How did everyone get on with the hashing methods? Was it challenging? Hashcat?
It was okay.
It was okay.
It was easier than the previous week, and probably easier than this week.
Yeah, it was. Yeah, I mean they vary in their difficulty and their challenge and things like that. I think it's a nice self-contained lab. You know when you're right with that one, and I think it does show the power of Hashcat. Hopefully, so hopefully you've all learned how scary Hashcat is, how powerful it is. Did anybody notice the data breach this week that appeared in the news?
It was something in Lithuania, wasn't it?
Yeah, it was 100,000, 110,000 government records.
SHA-1 hashed or something.
SHA-1 unsalted. You'd be shocked, honestly. You think that everything is amazing and fantastic, and especially in the public sector and the government, then you probably find that the systems are decades old. Right, so just find my presentation. I should be able to make a start. Good. Right, I'm just going to share my screen and hopefully you'll be able to see it. There we go. Okay, so thank you to those who have sent me their public keys already. At the end of the lab or somewhere in the lab, if you could send me your public key just to test, then I'll encrypt something for you back. And if you use my public key, then you should be able to send me something from there. But I'll explain that a little bit later. Okay, so in this lecture, we're going to look at a really important area for the future, and that's to look at public key encryption. So if you just mute yourself just now, if possible, but then if you've got any questions, then just come off of mute. There's no problem with that. Okay, so we'll look at some of the basics around public key encryption. Can everyone see my screen okay?
Yes.
Yeah.
Great. We'll look at RSA, which is still around and still well used, and then the new kid on the block, which is elliptic curve methods, and the one that's really crushing all other methods, and then just a little bit on discrete logs So those are the three main methods, but possibly what we'll find today is that quantum computers won't find these methods a hard problem anymore, and we could end up ripping apart the internet if we don't migrate. So near the end of the module, we'll be looking at what's called post-quantum crypto. Not to be confused with the post-quantum key exchange and things like that. Post-quantum crypto is crypto which overcomes the cracking of quantum computers. Okay, so that's our schedule that we're looking at. So really we are here. Week 5, Unit 4, looking at public key encryption. Next week we'll do key exchange and especially into the Diffie-Hellman method and elliptic curve Diffie-Hellman. For the guest lecture, we'll keep that kind of open just now, but we'll have hopefully someone in that unit, that slot. Look at the certificates after that. And then we have our test in week 9. So soon I'll get you really primed for how you might study for the test and when you can start looking at that. But we've got a bit of a buffer in the next few weeks to probably around week 7 to really look at the test in a bit more detail. And then in week 15 we have our coursework submission. It's a 50% grade for this and a 50% grade for our week 9 test. Does anybody have any questions about that schedule and what you're meant to be doing? Many people have asked me about the best way to study, and the best way to study is the way that you find best. So if you find doing the tutorial questions an effective way of studying, then towards the test, then that's fine. If you find doing the labs quite good for understanding some of the theory, but then pick up the studying towards the test, then that's fine. Really all that matters for the first test is the main methods and the theory behind what we're doing. Okay, so if you can manage to do the labs, you're doing very well. They are quite challenging. Someone asked me today how long they should be spending studying. Well, it's really up to you. When you think you've got 2 + 2 of lecture lab, then probably you're looking at another 4 to 6 hours additional study on average each week. But obviously that could be 8 hours one week and then none the next week. It's really up to you. Okay, so what we're going to look at, really the foundations of this was set up by Whitfield Diffie and Martin Hellman. And in 1976, they published a paper which really has laid down the whole foundation of cybersecurity, even to the current day. Within that paper, Whitfield Diffie presented a key exchange method that we'll cover next week, called the Diffie-Hellman method. And it's still used, but it's changed to what's called elliptic curve Diffie-Hellman. So it used discrete logs, but now it uses elliptic curve, and it's basically in the connections that we make to the internet. But within the paper, they created they outlined a method of a trapdoor, where it'd be possible to create a function where if you knew a secret, you would drop through the trapdoor, and then you would be able to reveal some private data. So they proposed it, and it was actually Rivest Shamir and Adelman who came up with the method in 1977 that is now known as the RSA method from that. So it was groundbreaking, and it was the first method that really implemented public key encryption. There were others. Merkel had actually proposed public key encryption to his undergraduate supervisor as part of a coursework, but his undergraduate supervisor gave him feedback that it was muddled, and he much preferred the other option that Ralph Merkel was producing. If you've ever heard of, has anybody heard of Ralph Merkel? Do you know what he? I mean, he did lots of things, but do you know what he did? What he's done? Ralph Merkel, anyone? No? Okay, we'll come back onto it, but Ralph Merkel created what's called the Merkel tree. And with the Merkel tree, you can build a tree of hashes. And this is the method that's used for blockchain. And what you basically do is you hash into another hash. These two merge into this hash, and these two merge into this hash, which means that I can prove all of the data elements in it just by proving the top level hash from there. So that was Ralph Merkel's main contribution. He wrote a patent which was about 3 pages long, one of the shortest patents ever, but it was completely groundbreaking. But Merkel did lots of other things, and it really had so many ideas that have been taken forward. Okay, so that's Rivest, Shamir, and Adelman there. And the strange thing was that they proposed that with their method, which uses prime numbers, they reckoned with 200-digit modulus, which is when you multiply the two prime numbers together, it would take 3.8 billion years. That hasn't been the case, and that we can now crack this level of RSA. So it just shows you that you think something is secure now, it might not be secure in 5 to 10 years. So you need to make sure if you're encrypting something that needs to be kept secret for decades and so on. So you need to understand that there might be weaknesses in the future. And it was in this paper that they outlined the concept of A and B, and we know them as Alice and Bob now. And Bruce Snyer obviously expanded on this and created a whole character set, including Carol and so on. So that's Alice and Bob, but not quite the Alice and Bob that we actually know. And it was the cypherpunks who came along, and on the back of the problems that we had in the 80s with the banks making massive profits from their customers, they came along. This was Timothy May, and Timothy May and the other chaps that just disappeared from the text there. But Timothy May and Hughes was the other one. Produced this agenda that eventually became the rise of cryptocurrency and blockchain, and looked at decentralizing our existing finance infrastructures. And they quoted that really our whole society will change, and there'll be an economic revolution all focused on public key encryption, zero knowledge proofs, and authentication and verification method. The day of the wet signature was going, and in the future we would see things signed by a public key. Okay, so really they were looking at the whole trustworthiness of creating systems that couldn't be tampered with, and which preserved the rights to privacy. And they reckoned that it would change the ability of governments to regulate things, to control their economy, to control fiat currencies, which is the normal way that a country would control its economy, through its own currency and its own trading. They reckoned that we could move towards a world that was completely decentralized and possibly didn't need banks in between. Okay, so it was defined as crypto anarchy at the time, and obviously there are many negative sides of this, and the Tor network is a good example of a network which there is a lots of bad things on it. But basically it's not the fault of the Tor network that it's used by bad people and criminals, because the Tor network itself is a very good technical solution for privacy, as we'll find out next week. Okay, and this was a classic quote. Just as the technology of the printing altered and reduced the power of medieval guilds and the social power, so will cryptologic methods fundamentally alter the nature of corporations and of government interference in economic transactions. So if you look now, does anybody know where Bitcoin is just now? What's it trading at?
Like 33k, 35k.
I think the last time I looked, it was about 50.
It's about 50. It's sitting at about 50 at the moment. Yeah.
Okay, and it's what we discussed last week. Had a big effect on it. Doesn't quite have the stability of normal markets, and it can be quite easily interfered at the current time. But we'll come back onto that, and I'll try and give you an understanding of what cryptocurrencies and tokens really mean. Okay, so let's look at a few basics first and understand where public key encryption is actually used. Yeah, hello. Oh.
Yes, question.
Yeah, go ahead.
That Bitcoin just right of Bitcoin. There will be no Bitcoin. In the down.
I'm struggling to hear you. Did anybody pick up the question there? Maybe we can pick it up later. Yeah, that's a lot better. Yeah, thank you. Go ahead.
I'm saying, I was asking whether is there a future for cryptocurrency, and can someone just wake up and write off cryptocurrency? Let's say Bitcoin, someone have a code, so just make Bitcoin disappear from the internet.
I didn't pick up the whole question there. You broke up at the end. So I think what you were saying is there a future, and as we'll find when we look at blockchain and this area, it's a token of one which is, you can have a cryptocurrency token, but you can also have an asset token, and you can have different types of tokens that can be traded. So it's a natural way forward to be able to trade with a token. So if I buy a car from you, then I prove that I own that car because you've signed a token related to that car to me with your private key. So we'll come back onto it. There are many changes going on just now. In Bitcoin is like a Ford T. It's like an old car. So we wouldn't have any cars just now if it hadn't been for the Ford T. It proved that you could have cheap cars that were produced, but we moved on to version 2 with Ethereum, and then on to blockchain version 3 with IOTA and other methods. So you shouldn't just see Bitcoin as the only show in town. It's not a great example of cryptocurrency. So I didn't hear the whole question, but maybe we can hold it back till we cover that as a topic. Is that okay? Right then. So what public key does is that you have a padlock, and the padlock is your public key. And then you have a key for that padlock that can open it up, and that's your private key. If you think about it, if somebody wants to send you a secret package, then you could distribute all your padlocks and allow them to be able to lock all the boxes with your padlock. And then once the box was locked, then no one could open them, not even the sender. And the only key that would open the padlock is the one that you have, which is your private key. So the private key is the one that's kept secret, and the public key can be distributed to anyone. So we end up with what's called a key pair, and we generate that, and we keep one secret, and then the other one can be public. The three main methods that we use to be able to use public key encryption is, the first one is to encrypt data. So it's possible for Alice to send Bob her public key. Bob then encrypts the data with her public key, and not even Bob can read the data here at all. The only key that will then decrypt the data is Alice's private key, and then she can recover the data here. No one should be able to read this data because it's the only key that would open it is Alice's private key. The other way that we can do this is that if we have a session key, such as with AES for a tunnel, and we want to get that key from Bob to Alice. One way we can do this is that, let's say we're talking to Google, then Google would send their public key to us. We generate the key that we want for the tunnel or for the session, and we'll encrypt that small key with Google's public key. We can then send that over, and then Alice will use her private key to be able to decrypt that, and then both Bob and Alice will have the same shared key that they can then use symmetric key encryption to be able to communicate. The weakness of this method is that if Eve has been listening to all the communications, then if Eve eventually discovers Alice's private key, then Eve can now go and decrypt all of the sessions, because she can now decrypt that. We'll cover this more next week, but this is to do with forward secrecy and to make sure that a single breach of a key doesn't reveal all the previous keys that we have used in the past. And I'll even give you a demo of Wireshark, where you can easily load the Wireshark up with a key that you've discovered, and for you to unencrypt the whole encrypted session. The main place that public key encryption is used is in proof of identity. And with this, Alice wants to prove that she really is Alice. With this, she will take some data and then sign it. So it's likely to be a hash of some data. She will then encrypt it with her private key. She sends that over to Bob. Bob then takes her public key and then decrypts that, and should end up with the same data that we have originally. In this way, Alice has signed with her private key that it was her that actually sent the information.
Oh, thank you.
And every time we connect to the web, this is basically what's happening. If we think of Alice as Google, then Google will send their public key to prove their identity and that they can sign with their private key. Okay, so we'll cover that more when we look at digital certificates. So the three main methods that we use for these public key methods: integer factorization from RSA, we have two prime numbers and we multiply them together to give what's called a modulus. The difficulty in this is to find the two prime numbers which make up this modulus. And if these are large enough, it becomes a very computationally difficult task. But unfortunately, quantum computers can easily crack that method. We can have discrete log methods, and one of them is LGAML, but not used that much. And then finally, the method that's most often used these days is elliptic curve methods, which is used on the Tor network, Bitcoin, IoT, smart cards, you name it. It's fast and efficient. As we increase the security here, it gets longer and longer to create key pairs. If we do it with elliptic curve, it doesn't really have a large overhead from there. So elliptic curve is virtually winning all the time. And if we look at our cost budget to crack, then we could certainly afford to crack a key by the energy that would take to boil a pool. So anything with a modulus of 745 bits and less is going to be easily crackable by law enforcement agencies. Anything above becomes a bit more difficult because it's going to take a lot of energy, but really we need a margin, and 1K RSA keys is probably the limit that we're looking at here. So we want to keep away from there. So 2K keys for the modulus is where we start normally these days, and most certificates on the web are 2K keys, which means that we need two prime numbers of about 1,000 bits from there. But we can see here the security improves, obviously, the number of bits that we have in there. But as I said, quantum computers will kill this completely. And there's one paper that says in a post-quantum world, the size of your public key needs to be 1 terabyte. Just the public key itself would be a 1 terabyte in size for your public key. So if I sent you my public key, it would be 1 terabyte long to make sure that we had enough security in there. So we can see the problem that we're going to have with quantum computers. It will really break much of our methods. And this is the state of the industry when it comes to cracking these RSA or the prime numbers. Remember that Ravesh said that for 200 decimal digits, it would take 1 billion years. Well, that was cracked in 2005 from there. So we're up to about 768 bits as a challenge. So we're starting to creep up towards the 1K level of factorizing these moduluses. Okay, so RSA is all about taking two prime numbers, P and Q, multiplying them together to give what's called a modulus. The real genius of it is this calculation here. If an intruder can find out what P and Q is, they can multiply P minus 1 times Q minus 1, and this will allow them to crack RSA from there. So we need to make sure that the prime numbers are random and they're not guessable because it will significantly reduce our security. Okay, so the RSA method, I won't go into any detail just now, but you take two prime numbers, you work out the modulus. You then, if we take 3 and 11, we end up with a modulus of 33. So our encryption key becomes a value E and N. The first thing that we do after that is that we calculate what's called phi, which is P minus 1 times Q minus 1. And it's this thing that keeps the security overall. If we can determine this value, it's easy to crack RSA. Even if we know one of the prime numbers, it significantly reduces the overall security. So in this case, it's 2 times 10, which is 20. We get a value there, and what we need to make sure is that E and 5 do not share any factors. So the factors of this is 2, 4, 5, and so on. So we can pick a value of 3. Then we need to find the value of D. where we multiply d times the e, and then take the mod of this, and we want that to equal 1. In Python, it's one line of code. It's called an inverse mod of e. And in this case, it's easy to see that because 7 times 3 is 21, mod 20 equals 1. So our encryption key is 33, and our decryption key is 33. So to go ahead, we basically take the message, raise it to the power of e, mod n, and then to decrypt, we take our cipher, raise it to the power of d, decryption key, mod n. And we can see, hopefully in this case, it all works out. Our cipher is 26, we take 26 to the power of 7, mod 53, and we get 5 back there. So in this case, we should be able to show that we can cipher with the e value, and we can decipher with the, with the d value. An example here, it's just some examples there. We can pick our e value, and then we end up with the d value, and the whole thing should work out. We can encrypt, cipher, and then decrypt and get the original value back again. Okay, so that's the RSA method, and I've got some demos on the website that you can actually have a look at. So OpenSSL allows us to be able to generate these keys, key pair. In this case, it's 1000 bits, and we output into what's called a PEM file, which looks like this. So this is good because it's nice and structured. We should all see this begin and end. This is the private key, so it should never be revealed. Because it's RSA, both the public and the private key are in here. Although it says private key, it has the key pair in this. But when we're using it, we would export only the public key from here. When we list the key in text, there's the modulus, that's n. There's the e value, and that's always used with RSA. It's always 65,537. This is the d value here. You see it's a lot bigger than that, but the same length as that one. And this is p, and this is q. So look at p and q. That's that times that gives that. So if this is 1000 bits, then this is 500 bits and 500 bits there. Okay, so that's how we generate our RSA key. And then when we're ciphering, we normally convert it into a base64 format so that it can be transmitted through a text channel in there. So this shows us a message, and then all of this is our core message. You've got to watch because there is new lines at the end of each of these, and when you build it back up into a single string, you've got to put the new lines back in. You can't just paste them in to make it into a string. Anybody any questions up to now?
Hi, Bill. Yes, I do. It's on the modulus. So you said, so 3 times 11 is 33, obviously, and that value is called the modulus.
That's right, that's that.
Is that different to the mod function, or is that the same thing?
Completely different. Good question.
Right.
The modulus is this value here. This is the modular n, mod n. This is a different function. This is the remainder from a division by n. This is n. There. Does that explain?
Yeah. So one of them is the multiplication, and the other one is the remainder after a division.
Not quite. One is mod n, which is the division by n to give us the remainder. The other one is the value of n.
Okay, so the term, sorry, I'm just confused by the term. So the term modulus, is there a modulus and a mod, or are they both called modulus, or is there only one thing?
a mod is the mod operator, or this percent. So it's an arithmetic operator.
Right.
It's a mod function. The modulus is this value here.
The modulus is the value.
Yeah, it's confusing, and I appreciate that. Yeah. Sorry about that.
No, not your fault. Thank you.
Okay. Pesky Americans, we'll just say it was their fault for coming up with all these names. Okay, so how do we make sure that this all works? So to make it easy, Bob typically has a keyring where he'll store his own private key, and he'll store his own public key, and then he'll get public keys from everyone else. So all he has to do is send an email to Carol, and it'll automatically pick up Carol's public key from his keyring. He doesn't have to keep downloading it. As we'll find, the keys have got to be passed in a trusted way. So we bring in Trent to sign the public key. So if Bob trusts Trent, then when he receives the key, he knows that Trent has verified it. We can also get it from a trusted authority. Not a lot of people do that these days, to post their public keys on a trusted place, but you can obviously go to a trust authority and get your keys there, and you know they've been checked from them. Okay, so the method that's really crunching them all is what's called the elliptic curve method. I won't go into the basic maths of it because that's not really that important, but if you're interested, then you create a function such as that, and it creates a little curve. Then you bring in a prime number, do mod p, and it ends up being points. At the core is that we have a base point called g on the elliptic curve, and then we create our own private key n, which is typically a 256-bit value. We then add g n times. So with elliptic curve, we can keep adding a point to another point, and we'll always end up with a point on the curve. The point at which we get is then ng, and this becomes our public key. N is a private key, g is the base point on the curve, and ng is our public key. We can show everyone this, but because of the computationally difficultness of this, even though you know that and that, you cannot determine that value. But with quantum computers, then possibly that will go too. So two of the most popular curves around is Satoshi Nakamoto selected SEPT 256K for Bitcoin, so it's well used, and Tor uses a curve called curve 25519. But there are many other ones, and there was one developed by NIST that might have had a backdoor in it, and you'll probably find from Bruce Snire that he doesn't trust NIST to define these standards properly because there might be backdoors in them. Okay, we'll come back onto this when we look at Bitcoin, but basically you create a private key. From the private key, unlike RSA where you create the keys together, you then can easily create the public key from that. That's a 512-bit key point on the elliptic curve. This is typically 256-bit, and then those are this is the key pair that we have here. When we put something on, when we sign something, we sign it with our private key, and then we prove it with our public key. Okay, so here's an example of a Bitcoin transaction. Bob wants to pay Alice. Alice is a private key. She creates a public key from that, and then creates our Bitcoin address. Bob puts that in the transaction, signs it off with his private key, and then puts that onto the ledger, and everything's fine. The transaction has happened. Alice can check because she knows Bob's public key, and he has now transferred money to her. So we can also generate elliptic curve key pairs, in this case for this key pair with OpenSSL, and we end up with this, but we can also display that in terms of numbers. You can see these numbers are a lot smaller than RSA. And you can see the private key is much smaller too. And there's the public key, which is about twice the size of that in there. Okay, and then we can export to give us our private key, just like that one. And then we can export to give us the parameters of the curve. In this case, we have a prime number. We have an A value, B value. We have the generator point G. And the order is the number of points that we can use. So it's almost like the range of the private key is defined by this order value. But everybody knows about the elliptic curve and everybody uses the same one. But you've got to watch, because there can be bad implementations that can really rip open your system. So we'll find that it's used in what's called elliptic curve Diffie-Hellman, where each node negotiates a key with Bob, and then we create an onion around the data so that the first node decrypts the purple layer, second node will decrypt the green layer, and then the third node will decrypt the red layer. But these keys are negotiated through elliptic curve Diffie-Hellman methods. The data here is unencrypted, so we typically overlay encryption and have an HTTPS connection, which means that that data will still be encrypted when it reaches a gateway. This is the gateway out of the Tor network, and everything in here cannot be traced back to Bob or can be seen for the data. Okay, so a popular curve is curve 25519 that we'll cover more next week. As further reading, you can go and read some work on the Elgamal method, which is the encryption method that uses discrete logs. We don't really use it that much. It is used for signing, and we have a method called DSA and elliptic curve DSA, and that uses a derivative of the Elgamal method. So it's still used in some way, it's just that we don't use discrete logs anymore. We use these elliptic curve methods. As a final point, let's look at a more complete picture, and this is to use PGP encryption, where we can sign for an email and make sure it's been verified. Initially, Bob takes a hash of the message, encrypts with his private key, puts that hash, encrypted hash, along with the message, and then generates a new session key, which will be a symmetric key, and then encrypts the whole thing here. Then takes Alice's public key and encrypts the session key and adds that into the email that's going to be sent. When received, Alice will take her private key and then is able to encrypt the session key for the email. With that session key, she can then open up the box and read the message. She takes her own hash and then will decrypt the hash with which key. So for this encrypted hash here, which key will Alice use to decrypt that?
Bob's public key.
Bob's public key. Okay, so she gets that in a trustworthy way. She takes Bob's public key, she can then decrypts and then compares the hashes together. And if they compare, she knows that no one else has read the email. Bob was the one that sent it, and it hasn't been changed in any way. And this is the way that we can use our hashing methods, our public key encryption. And look here, we're not using public key encryption to encrypt that. We're only encrypting the little key that we have here. Okay, so that's been a quick overview of public key encryption methods. I hope that was useful and gave you an overview. I can see that we have the professor with us already for our session. So I just ask, is Adrian on the call yet? No.
Yeah, I'm here, Bill. I've been listening to your extremely comprehensive talk of elliptic curve encryption.
Yeah,
and
it was quick. Yeah, I'm a big fan of elliptic curve cryptography, as Alan knows. but obviously it's under great risk. So I hand over to Alan. I think, Alan, you've got some slides perhaps that you want to share. Oh, you're on mute, I think, perhaps.
Yep, well, hello everybody. I wanted to, now I think I can only share if somebody allows me to, because at the moment it won't let me share anything.
Right. Okay.
Who's in charge of the meeting?
It's me, and I'm sure I enabled that. Maybe because you're a guest coming in. So just let me see. Does anybody have any initial questions? Oh, there we go. Yeah, people there. Everyone who can present. Everyone save. That's it. Do you want to go ahead?
I'm a presenter, right? Okay, hoorah! Right, now let me see if I'm going to find the right thing. Right. So, can people see that? Is that showing up, Bill?
Yep, perfect.
Right. I mean, it's really just a sort of throw a pebble in the pond. Very clever people like Bill come up with all these crypto schemes, and then people like me come along and try and break them. And one of the interesting things about the whole of public key encryption, where we start off from, the stuff that Diffie and Hellman came up with in 1977, that is. Got to remember, you're all very young. And then obviously because of you needed to have proof, that's where the RSA came along, so they could have the signatures as well. And then because of the length of the RSA keys, everybody then started favoring the elliptic curve method. So if we just focus on the RSA method for a moment, I mean, fundamentally, it's based on the fact that it's very easy to multiply two prime numbers together, but it's a lot more difficult, computationally speaking, a lot harder to work out, if I gave you a number, what two prime numbers had been multiplied together in order to come up with that number. Now, there are ways of doing it. We've known for a long time, since Fermat's, Fermat's difference of squares principles, Euler's principles, 17 something or other. But probably the most advanced at the moment, certainly at the moment, is what's called the quadratic sieve. That wasn't developed until the 1980s. But even then, if you look at some of the speeds, let's suppose you just go, we're talking about RSA again, something approaching a 600-bit RSA numbers, as Bill was saying. Actually, these days, of course, they're much larger than that. Typically, it used to be recommended 1024, and now everybody's on to 2048. But even with a couple of i7 processors running full tilt, it'll take you 3 months to factor that. And all you need to do is add another 10 bits to it, and nobody's ever been able to do it within a meaningful time frame. So it all relies upon that idea of easy to do one way, but very difficult to do the other. I have to say, one of the things that's always fascinated me about this is there's no formal proof of that, which is something that's always worried me slightly. But it became even more worrying back in '96 when Peter Shaw came along. A brain the size of a planet. I don't know how he came up with this, and that he in fact, so good was he that he now has Shaw's algorithm named after him. It was his quantum algorithm. You can actually see the algorithm on the blackboard there behind him, and his paper. But basically, it was based on that very early, 1760. There you go. Euler's method from 1760. Don't need to bother you with really how it works. But what Peter did was he took Euler's method and he reduced it down to the point where actually what you were trying to do, never mind the modular arithmetics and the greatest common denominator calculations, etc. All you need to really know is that if you think about it in a flowchart, being a computer scientist, I put everything in flowcharts. It's this bit in the middle. Find the period. That's the bit that suddenly quantum computers were able to do much faster than anybody had ever been able to do it before. I mean, you can actually run Euler's algorithm. You can run Shaw's algorithm, which is this, effectively. You can do it in an Excel spreadsheet. But it'll take you forever to actually come up with any answers, of course, if you've got any kind of significant numbers, as per the modern RSA implementations. But then what Peter realized, Peter's real contribution to all of this was he helped develop what was called the quantum Fourier transform. Now, anybody that's been involved in signal processing will know that what a Fourier transform does is it takes a signal and it converts it into the frequency, i.e. it finds the period, it finds the frequency of what it is you're doing. So Peter said, well, hold on a minute. We're trying to find the period. We're trying to find the frequency. In the middle of all of this, there's this thing called R, the period R. Think of it as the frequency. What if we did that with a quantum Fourier transform? And the answer was, yes, you can do that. And sure enough, that's what it looks like. Now, the reason the quantum Fourier transform is much faster than standard Fourier transform, I mean, going back when I was a baby physicist and then doing my postgraduate stuff, I did a lot of it in signal processing, and we worked on things like fast Fourier transform, discrete Fourier transform. There are all sorts of optimizations there. Effectively, quantum Fourier transform takes it a step further, and it does in the same way that the fast Fourier transform keeps the results and reuses them as a way of speeding things up. The quantum Fourier transform does all sorts of things in parallel. Effectively, you can think of it like that. If I get into a deeper discussion of it, you'll realize fairly quickly that it's not actually just pure parallelism that's going on here. But think of all the possible numbers, all the possible answers, and it can compute those. But the really tricky bit, I won't bore you with some of this, is how do you get the answer out? Because the thing about quantum computing, throughout all of quantum computing, everybody will talk about the fact that you can operate on qubits, quantum bits, when they're in their quantum state. But at some point, you've got to get the answer out. And whenever you compress it down, you actually cause the thing to collapse and actually get the answer. You only get one answer out. So it's got all these answers in there, but you cause it to come down and say, I want an answer now. It'll only come out with one. And again, the part of the genius of what Peter did was that the last couple of steps here in this, it is a thing called continuing fractions, which if you ask me to explain it, my head will explode. But effectively, you get one of the possible answers comes out when you measure it. And if all you have to do, because it's so quick to multiply again, you check. You actually do that. It says your answer is 5 times 3 when you're trying to factorize 15. You can very quickly check, is that the right answer? If the answer is yes, that's the right answer, then you've got the answer. If not, you try again. And it's so quick that effectively you go around that loop like that. And in fact, you know, I won't bore you with it now, but you can go through simple quantum factoring of something like 15 and prove that it works. As I say, continued fractions is really the key to all of this. There is a one of the Surrey guys has got something, tries to explain it to it, but it works. I'm an engineer. It works. But the downside is, of course, you've got to have a lot of qubits. Just the 4-bit number takes something like 8,000 quantum gates. Now, quantum gates take, I mean, if one of the things I was going to do was jump out of this, if I can. Now, how do I jump out of there? And I was going to show you something I was actually working on earlier today. Now, can I share this? Am I still in the meeting? Right. Oh no, my sharing option seems to have gone again. Share content. Nope, I'm back. Here we go. Right. Can you guys see that? Can you see that, Adrian?
Yeah.
Yeah. This is how I do my quantum computing. Through the cloud, of course, and IBM very kindly give me access. I'm part of there's about 60 of us who have access to IBM's quantum computers. But as you can see, even the best of them has only got 7 qubits. I think the simulation now goes up to 32 qubits, but the actual quantum computers that we work on and run our algorithms on is only 7 qubits. And if you think about, in fact, something again I was working on earlier on, where the sort of circuits you're talking about here, a gate. Imagine this is called a Toffoli gate. Imagine you drag a gate into that's one gate. That will take 3 qubits, or rather 2 qubits to implement, because you've got to have a control qubit. So if you go back to the presentation again and think about 8,000 gates for a 3-bit. A 4-bit factorization, you can see that you're going to have a much larger quantum computer than we have at the moment in order to put it to actually make this real and make the threat real. But of course, we all know that going back all those years, computers started off the size of a house, and now I'm talking to you one that you wouldn't even know it was there. It's under my screen. So the threat is definitely there, and that's one of the reasons why we've all started to move on. Now I hear you scream, "Oh, hold on, that's just RSA." But there's quite a one of the papers actually Bill and I did. There you go. I invite you to go and read a paper we did a few years ago, where actually we were asking about is quantum computing going to be the end of everything for this public key encryption? The answer is it depends if we can build a quantum computer. But what you find if you go through to the annex, you'll find the proof there that we did that actually it's not just the factoring problem, the factorization problem that these quantum computers can do. If you take Peter's algorithm, the quantum Fourier transform, and you convert it into something very similar, I think called the quantum phase algorithm, phase estimation algorithm, it turns out that the Diffie-Hellman, RSA, elliptic curve, they're all part of a common set of problems that require solving in terms of going back and getting your answer. They're called the hidden subset problem. And indeed, that Shor's algorithm can be basically generalized, and all of those become at risk. You can solve all of them, you can reverse all of them and get the results out. So for example, in the elliptic curve that Bill was talking about earlier on, where you've got the private public key, those 2 points on the curves, you can actually reverse that out. Again, it ends up being part of the discrete logarithm problem. So that's why everybody's so worried, because everything we've got at the moment that's out there, albeit elliptic curve has become more popular because it's shorter and everything, they could potentially be at risk. Everybody's saying, oh yes, but quantum computers are way off, but it actually does take some time to find out what the alternative is. And what NIST are doing at the moment is they're saying, right, we're going to have a competition, and indeed they're in the final round of the competition, I believe, where they're asking everybody what alternatives to RSA and elliptic curve are we going to have as the standard for public key encryption. And so that's where we're at the moment. We've kind of got I think we're down to the last half dozen. There were about 32 candidates, but at the moment, what everybody's trying to do is see, first of all, are they quantum resistant? Will they withstand it, or are they going to find, like Bill and I wrote in the paper here, that actually it's just there's another way of looking at it, where the same old derivative of Shor's algorithm will solve the problem, or are they truly going to be quantum resistant? So we find ourselves teaching a lot at the moment about public key encryption and public key cryptography, but of course, some of what we're teaching now, in 10 years or 20 years, it may no longer be viable as a method of encryption. So it's all about, we're on the cusp. And so I really wanted to sort of have a bit of a discussion this evening and see what people thought about that. See whether they, the ideas they have about whether they think it's a real threat or not. So if I go back to that, I think I can stop sharing. Yes, stop sharing. There we go. Great. So over to the floor.
I'll hand over to Adrian, who will chair this this session. Adrian?
Thanks very much. That was fascinating. I'm always very interested because we work very closely with Bill, and Bill is kind of preeminent in the crypto and everything to do with that. One of the questions I have, it's more of a political kind of understanding, is that one of the issues that we have at the moment, there is this tension between nation states who want to know our information and everybody else that don't want to share it. And there was, if you remember, a little while ago, that the US decided that they would put that little chip inside every TV so that they could understand, the V chip, so that they could understand exactly what you were listening to and watching. And there is potentially a little parallel here, because only nation states will be able to afford, in the very most recent future, quantum computing that could ever reach the number of qubits to be able to decrypt what we want. So if you're a China, or if you're maybe a Microsoft, or if you're a Google, you could probably afford a machine that would be able to decrypt this. Certainly, if you're GCHQ or if you were NSA, you probably already got one working quite happily in a back room somewhere. So one of the questions I have is how do we protect against that? And what are the algorithms that are going to be quantum hard that will be implemented potentially by software companies that are actually maybe working on both sides of the fence?
That's a really good question, Adrian, because there's been a huge debate, but I have to say I'm old enough now that I remember having the debate probably 4 times already since the late 90s, since Clinton's era, when he was president, and they proposed putting the Clipper chip, if anybody remembers that, into all the computers, which basically had the master key in it, and you could unlock everything. Now, there are only a fixed number of ways. I help Europol, the European Police Agency, and we wrote about this not so very long ago, reiterating again to the politicians, there are only a certain number of ways you can deal with encryption. You can have what's called key escrow. So you could, every time you create a public-private key, you put a copy of that private key into some file somewhere, and then somebody with a warrant can come along. But of course, all of the systems that people like Bill will talk about actually have what's called perfect forward security in them, in that there's a new key created for every conversation. Can you imagine storing the keys for every WhatsApp conversation or whatever? It's just not practical. There's I suppose it's the key under the front door mat analogy, where you've got the master key. But the problem is, I'll give you a really good analogy here, actually, where Transport Safety Agency in the United States, whenever you go to the United States, if you've got a lock on your luggage, it's got to have one of those standard keys on it that only the TSA can unlock. Well, you can buy those on eBay now. So what's the point of the lock? So that's what happens with master keys. They get stolen, they get copied, whatever. You can then potentially weaken things, and that did happen actually very early on. Bill was talking about PGP. Early on with PGP, the United States was so worried about it that they classed it as munitions and said it couldn't be exported. But all that happened was they literally printed out the algorithm and took it across the border into Canada, and it became PGP International. And we still live with the legacy of some of that, because there are some weaker cipher suites, for example, in our browsers. Well, they've done it. And there used to be attacks where you could cause people to downgrade to it. And so if you weaken encryption in any way for your enemies, you're doing it for your friends as well. So it's always then subject to those downgrade attacks. So none of those ways really work. I mean, we know they don't work. They've all been tried before. People have sort of gone through routines, and they don't work. Interestingly, what's happened in the UK now is the legislation has been changed, where certainly the last lot of legislation that came in, what's called the Investigatory Powers Act, when they drafted that, I had long conversations with a guy called Robert Buckland, who's actually my neighbour, who drafted it. He's now whatever he is, not the Attorney General, Lord Chancellor. And he was all about, do we just make encryption illegal? And I said, well, it's pointless. You can't do it. I mean, you can't do that. So actually, in the UK legislation, what they've done is they've gone for an alternative approach. They've recognised there's no point in trying to crack encryption. It'll just get more difficult. You won't do it. But secondly, only outlaws will use it. And what are you going to do? If you banned all the apps, people would simply write their own. So actually, in the legislation, they've introduced a totally different concept called the rather euphemistically termed equipment interference, which basically means if I want to listen to your encrypted conversations or read them, I simply bug your device. So I send you a little bit of malware and it reads it outside the encrypted channels. So it doesn't bother going into the encryption. It actually reads it outside it. So that's what encrypted equipment interference is all about. However, we have come round the boy again, and I noticed Priti Patel signed a letter with the so-called Five Eyes countries plus Japan and India, saying, oh, this is terrible, and all the emotive things that come up about, child abuse and criminals should have no safe place to hide, which is true. We agree with that. But there are some facts of life. And I remember having a very interesting dialogue with the Australian Prime Minister where he was going on about, no, it's the laws of Australia that should apply, not the laws of maths. And I said, well, I'm sorry, but you can't undo the laws of maths. And, people will apply it. So these concepts that have been there before, weakening, key escrow, we know they don't work. So it's quite interesting that there's been some later ones that have come along. The one that's closest to what you were talking about earlier, Adrian, is a thing called crumpling, encryption crumpling, where you don't weaken it so much, but you accept that maybe when quantum computers come along, that it will be able to crack it. But of course, only people with the resources to do it are going to be able to do it. So that means nation states, intelligence organizations, people like that. But I think an awful lot of cryptographers would say, well, crumpling is kind of accepting that you're weakening it. It's sort of the corollary of, I know it's going to become weaker and I'm just not hardening it. So personally, I disagree with that. But then the most recent one, and I was talking to them only today, a guy called Ian Levy, who's the Chief Technology Officer at the National Centre for Cybersecurity. He proposed a thing called the GHOST protocol, with so-called exceptional access. Now, the GHOST protocol is basically going back to the pre-Snowden days when you didn't have end-to-end encryption, in that, and I'm sure Bill goes into all of this in his course about how TLS, for example, you can encrypt from your browser or from your whatever your app is to the server, and then from the server to the other party in the conversation. But whilst it's on the server, it's not encrypted. And so you can sit on the server and listen to it. The very reason end-to-end encryption came in the first place, because Edward Snowden revealed that actually that's exactly what they were doing. So what people like Facebook, bless them, or WhatsApp at the time, and Signal, all the rest of it said, well, even if someone comes to us a warrant, we can't, they could take a rubber hose to us and we cannot give them anything that will allow them to listen to your conversation. Ian was saying, well, hold on a minute. There is a way of doing it without us sitting and listening to the unencrypted conversations with the so-called GHOST protocol, where effectively you, WhatsApp or whoever, we come along and you make us a silent partner in any conversation, which is perfectly possible, of course. You can architect the apps so that it does that. And they come along and say, I want to listen to the conversation between Bill and Alan. So every time Bill and Alan set up an end-to-end conversation, it's end-to-end encrypted, but they join in as a ghost in the conversation. And that's the latest proposition that's out there at the moment. So it's interesting that all of them are not really the ones that seem to be getting traction. That is getting some traction, the ghost protocol. They're not about sort of trying to tackle the encryption head on. They're recognizing that you're never going to beat that. They're looking for ways around it. They're looking for the sort of side channel attacks, if you like. So I suspect that's where it's going. And it will probably then be a whole argument about, well, who's allowed to go along to WhatsApp and Signal with the warrant and say, which government? Is it just the US government? Is it the UK government as well? Is it the French, the Chinese, the Russian? Who's allowed to go along? And of course, the Americans have got a very American-centric view of it and say, well, of course, the American government should be allowed to go along to WhatsApp. But of course, why is that any different to the Chinese government or the Russian government or the Polish government being able to go along and say the same thing? So again, it's politics. It's not science. So a long answer to your question, but there's a huge amount of discussion in there.
I think this one is going to run and run, and it's certainly not over. We do have a question. Robert Hunter has just basically asked, he's on mute, but he'd be interested to know how much of quantum computing is theoretical versus reality now. Is there a 50 to 100 qubit quantum computer? The IBM Cloud and AWS bracket may not be that well advanced. So, I mean, looking at from my own experiences, I know that the machines that you can access now, like the ones that you showed us for 7 qubits, are not necessarily the same level that you can probably get a state-of-the-art that the nation states are using in the back office.
Well, Google is, yes, again, very interesting, because Google said that they thought they were going to have a 50 to 70 qubit processor ready by the end of last year. It didn't quite happen. But there's a dark horse. There is a bit of a dark horse in all of this, because the qubits, if you think of the qubits physically, a lot of them are they're things like, effectively they're measuring electron spin, things like that, and they're very subject to interference, because to stay in that quantum state, any kind of interaction with the real universe, it collapses, and you go to that, you get an answer even when you don't want one. So there is a dark horse, which actually is Microsoft's been doing most of it. They've got a place called Station Z in Santa Barbara, with a lot of funding from various people, including Google, which is looking at a thing called topological quantum computing. And that doesn't need to use qubits in quite the same way. So it's not dependent on sort of having masses of qubits in quite the same way. One of the problems with that, even with like having a 4-bit number, Shor's algorithm having over 8,000 gates, so goodness knows on how many qubits to do it. You actually do need redundancy even in that, because you've got to have some error correction because of all the interference. Topological quantum computing, it turns out, is a lot more robust. They didn't think it would work because it relies upon a particle that, I remember years ago talking to Bill, it must have been about 2010 or something, and we were talking, and that I was saying, I don't think it'll ever happen. And then, jigger me, 2 years later, they actually did discover the particle, I think called the Margarino particle, which actually could make it possible. So there's something coming up on the rails there that might actually sort of bypass all of this. And as people are struggling to get that 50 qubit processor, you might suddenly find there's a totally different way of doing it. So one of the things that being in computing for so long, you remember that things suddenly come out of left field and change it. So it's a really good question in that we're all struggling. I mean, IBM is one. Actually, they do have some of the most advanced. I would say that, wouldn't I? Because I use their processors, but they do have some of the most advanced stuff. But even those, I mean, like the one I was using today, the reason it's so difficult is because actually it's not the processor. It's not the fact that those 7 qubits are there, those Josephson junctions on a chip are there. It's the fact that when you see it physically, here I am sitting in my house using it in comfort, but actually the thing itself is operating at almost absolute zero inside an incredibly shielded room. And it's that engineering that takes a lot of the effort. But if this topological quantum computing starts to happen, things might suddenly zoom past and come in from the side. So it is a reality. It's there, but it's nowhere near enough to be a current threat. But never say never. Never say never. All the time, I started off as a baby physicist, and my tutor, his tutor had been a chap called Richard Feynman, who actually was the one that originally proposed quantum computing. But ever since then, everybody said quantum computing is 10 years away, but it's always been 10 years away. So I think you're probably safe in saying it's 10 to 20 years away, but which 10 to 20 years, I don't think you can say. But you can't take any chances, because just think what will happen if one of these things comes up on the outside rail, does suddenly do it, and there's no answer to it. Everything that we're dependent on, and we're using it now, public key encryption for establishing the keys for this call, suddenly it all becomes redundant. So that's the thing. That's why everybody's desperately trying to find the alternatives right now, because it's not that big right at the moment, but it is still it's a threat, but it's not actually that viable at the moment. So it's a good question.
I always think that these things are driven by necessity. I don't think that the world has managed to evolve a critical mass that these things are front and center. But should we have another major conflict where people are using encryption, I could most definitely see that this quantum computing to make sure that somebody had the edge if they don't already.
That's such a good point. I mean, it's a horrible fact of life, but wars accelerate technology enormously. And it's quite interesting as well. One of my little bugbears is, as interested as I'm in quantum computing, one of the problems is the thing that's actually driving it at the moment. There's a real misnomer out there. Everybody says, oh, we're all right. Everybody's probably aware we're running up against Moore's law. What do? We can't get we can't squish any more transistors onto those wafers. And so, and everybody says, oh, quantum computing, that'll be the answer. That's, we'll go from classical computing and move on to quantum. There's a huge problem there. And it's the elephant in the room, which is quantum computers are not general purpose computers. There's only about 4 types of quantum algorithm. It so happens that one of them will break modern quantum cryptography, and that's why so much money is being poured into it by the likes of NSA and whoever else. But actually, as a general solution for things, it's not very good.
I mean, one of the things, you're absolutely right, and when they hear about quantum computing and how fast it is, because it can break the NP problems, the stuff that classical computing, as Bill rightly says in his, these will take thousands of years. In fact, some of them will take you more seconds than the universe has existed to try and break. But a quantum computer, actually, that could, break it quite quickly. And the challenge that I think that we have is to try and understand, from a general public point of view, that you will never be able to run your Xbox off a quantum computer. So that will never happen.
I'm not going to be doing my word processing on my spreadsheet on a quantum computer exactly. And to show you how sort of specific they can become, everything I've been talking about today is what's called gate-based quantum computing. There is another type of quantum computing, which is called adiabatic. And those exist. You can buy one now, and they are in use. And they're very, you talk about longer than the age of the universe to solve some problems. Take something, a really simple problem that, you know, all baby computer scientists are taught, and we're all talking about the traveling salesman problem. And you only need to get to, say, 22 cities, and solving the problem takes longer than the age of the universe, which sounds bizarre, but, you know, it is one of those problems you just can't solve. So it turns out that they're optimization issues. So how do I find optimize? There is this other type of quantum computing called adiabatic quantum computing, is very good at solving those type of problems, for example, and indeed does solve the traveling salesman problem. So much so that people like Google and the US Navy have bought these and are using them for actually looking at other optimization problems. So things that effectively are about, can I define it in an equation, which then I find the optimal solution for that equation? That's the answer. So if you can pose, it's all about how you pose the question. But those kind of computers, Geordie Rose, who's the CTO there, he will bang on endlessly about, you know, he's got a quantum computer, he's got a chip there with over 1,000 qubits on it, but it doesn't work in quite the same way as the one that everybody wants to work, because it's the other type that runs Shor's algorithm. And that's, as I say, exactly as you say, really the driving force behind is that they want to break encryption. They want to break public key encryption.
Yeah, I think that's the hot ticket at the moment, because you know, we are moving into a much more world, and you see this very recently, you know, into kind of look, you know, from as a consumer to look at the different organizations and the way that these big mega, you know, Apple, for example, and Facebook, you know, Tim Cook faced off directly with Facebook, and you saw the very different of opinion. Apple really trying preserving the ownership of data for their consumer, and Facebook basically want you're the product. Well,
there's an absolutely fascinating sort of discussion needed. I'd be really interested in what the students think about this, because I come from a different generation. The students, I suspect, if they're younger students, come from a generation where there's this funny social contract where there's no such thing as a free lunch. So if something is free online, just as you said, Adrian, actually you're the product, or rather your data is the product. And privacy matters. Now, Apple, because of their business model, they want people to buy their hardware. We'll buy iPhones or iPads or whatever. That is dependent on them being able to demonstrate that your data will be kept private, and privacy matters to them, even in the face of law enforcement coming along with search warrants like the San Bernardino case and things like that. However, someone like Facebook or Google, you're the product. So actually they want your data to be the least private it can possibly be, because they want to exploit that data. So that's why, interestingly, it's all about the business. Read Facebook's terms and conditions. They're really very simple. They say, we sell your data to make a profit. It's as simple as that. And that's the contract you enter into with. If you read the terms, you're agreeing to those terms and conditions. So I'd be quite interested in what the students think about. Are they actually happy with that kind of social contract? For example, the corollary would be, would they pay to use a social network? Or are they only going to use a social network or a search engine if it's free? In which case, are they happy that they're being exploited? Their personal data is being exploited. I come from a generation where I'm not happy about that at all. But actually, you talk to my kids and they're a lot more comfortable about it. And you think, oh, you know, and I don't think you should be that relaxed about it, because you give privacy away, you don't get it back.
That's absolutely right. I think that we've got some. Okay, we've got another one from Robert Hunter. I'm finding it difficult, actually. Apparently, Bill just told me there were 10 comments in the chat that I'm not able to access at the moment. But Robert's made another comment. He says your nation state point at the beginning was very interesting. I wonder if there is an arms race here. It feels like Kennedy's race to the moon. We don't do quantum computing because it's easy. That to me would be absolutely the nation states probably falling all over themselves to make sure that they can crack your intelligence quicker than anybody else.
Well, I can give. It's not quite quantum computing, but yes, to show that is happening. Obviously, most of the stuff that's actually happening won't be in the public domain. But to give you an example of something that's in the public domain, quantum key distribution, which is sort of, if you like, the quantum technology answer to the problem, where you do key distribution using quantum principles that mean that you can be sure that the key is secure. There's definitely an arms race going on in that. The UK government has funded quantum technologies to the value of 290 million. We're building our own quantum key distribution network in this country, which most people don't realise, all based on fibres. The Americans are sitting there saying there. And then all of a sudden they said, hold on, because what happened? The Chinese launched a satellite, which actually did a form of quantum key distribution, because everybody before that had said it's not possible. They've got one up there. It's been there for 2 years, 3 years. And it's happily working away. So they've kind of, again, people said it can't work. And then suddenly somebody did it. And so all of a sudden the Americans are saying, we've got to do this now. And I had a very interesting conversation the other day with a government agency about a thing called quantum radar, where, again, they said, it can't work. It's never going to work. And who's going to want it? And all of a sudden at one of the air shows in China put up a thing saying, well, we've got quantum radar. There it is. So all of a sudden, flat panic. What the hell do we do now? It's one of those things where you're right. I think there's a whole series of these things going on where people think it's not possible or it's not viable. We've got to do something. In the field of public key encryption, we've got a big problem, because if it ever does come tumbling down, then just everything's. I mean, our daily lives are so dependent upon it. Every time you make a phone call to go into your bank site, it's everything Bill's teaching the guys is, it's, if we didn't have it, and most people again don't realize it, I don't think they realize what impact it would have on society.
Well, I think for a start, it would take down the entire finance industry. We have another question. We have a question from Peter Hollyfield. Are we ahead or behind the required timeline to beat the threat of quantum computing? Taking into account protocol definition, implementation, or adoption?
Really good question. I think we probably stand a chance of being ahead of the curve, because NIST, this is all because, again, NIST, the National Institute of Standards and Technology, I always get that wrong. Again, if you go back a few years, the story with, there was a thing called DES. Did you cover things like DES, Bill, when you do encryption? Yep. I mean, go back to DES in the 1970s, when old duffers like me were doing encryption in government, that was that was it. That was the de facto standard, based on a thing from IBM called Lucifer. But I can break it in a couple of minutes, or seconds, actually, probably on this computer in front of me here. So they had to find an alternative, and that's what NIST did, and it became the advanced encryption standard, which we all use today. It's the standard thing we use today for our symmetric encryption. So I think they recognized, in that case, AES, they recognized that what was coming, because things like DES just couldn't withstand the advance of computing. So I think we probably stand a chance if we get it right. And as I say, we're in the final round at the moment. In terms of implementations, what's really interesting is that, I don't know if anybody uses Chrome, for example, as their browser, but they might well have already been using a post-quantum crypto algorithm, because they had a thing called New Hope, which is one of the final candidates, which Google put in and as a trial and tested out. Nobody knew it was there. So a lot of these things might happen under the hood without people actually realizing they're happening. At least that's the hope. I mean, it should be seamless for users, but it's just that we'll have to teach the students a bit more about some of these, whatever becomes the new standard.
Daniel Crosley, he's mentioned one of your papers that you wrote in 2016. It says in that paper, the facts indicate that quantum computer capable of threatening public key encryption systems will exist by 2025. His question is, do you guys think this is still the case?
As I said, the trouble is you write those papers and it's always 10 years away. I remember the paper that Bill and I wrote, we thought 10 years, but 10 years seems a long time. And actually, it's a bit like when you look at modern computers. I mean, again, talk to a certain generation of people, the younger people today, and they think, what's the big deal about? I mean, I've got a laptop in front of me, 128 gigs. It's got a Xenon processor in it. I mean, it's like, Go back to when I started, even in the 1980s, and we had to be so efficient in our programming because we had 16K of memory, and the processor might run in a week. So we had to have special processors just to do floating point arithmetic. So things don't advance. You look at it and think, God, that since the 60s, it's doubled every 18 months. Wow. But actually, that's quite a long time. 60 years is quite a long time. So if you were to, from when it was first proposed in the 80s, if you were to project forward, I suppose, maybe 2040, something like that, you might start to see a viable quantum computing in general use. But up to that point, I mean, we don't know what's running in various organizations' basements, of course. And it's always going to be a closely guarded secret. But at the same time, as I was saying before, it's very easy for people to say this isn't possible yet, and then suddenly someone launches a satellite and it's doing it. So you don't know what's already there. But at the same time, 2025 feels a bit too close now. So I think I might change my mind and push it out a bit more.
We've got one from Devi Patanik. It says, do you see quantum computing enveloping the classical computing to provide protection?
No, is the honest answer. I mean, that's the big thing. The big point, if you take away nothing else, the fact that quantum computing is not a general purpose computer. It's a threat to what we've got as public key encryption at the moment, but it's not a general purpose computing environment. But secondly, as an answer to the problem, as I mentioned, in things like quantum key distribution, so as a method using quantum principles to protect, one of the reasons I don't think that's going to become mainstream is because there's too much out there already that you need to just change under the hood. If you started trying to, for example, quantum key distribution, everybody would have to have fiber to the home. What would you do on mobiles? There's all sorts of practical reasons. Plus, it's just expensive infrastructure. Whereas if you can come up with an alternative algorithm, so instead of using RSA or ECDH for your key exchange, you've got a lattice-based NTRU, for example, which looks like one of the favorites. My personal favorite is a slight variation on what Bill was talking about earlier, the elliptic curves. It's a thing called supersingular isogenies, which is a very particular type of elliptic curve, which it turns out is a subset of elliptic curves, but it does actually withstand that discrete algorithm solution that we mentioned. So, but it's kind of fallen out of favor. I suspect it'll be a lattice-based solution that comes out, but those can be retrofitted, if you like. So I don't see the quantum computing coming out as being a way of protecting ourselves against quantum computers, if that kind of makes sense. So quantum technology is not necessarily going to be the answer to quantum technology. I think it'll be about finding things that just don't happen to fall into this hidden subset group that can be solved.
It's very interesting. Actually, Franklin McGowan asked a very similar question to the one you've just answered. So maybe it says, could quantum computers be used to create keys resistant to cracking with quantum computers?
Well, one of the things, actually, you're hitting a really interesting subject there, because one of the things I'm absolutely fascinated by is randomness. And of course, again, Bill will go into all about the seeding of all these things and producing random numbers. And of course, we rely upon computers to produce random numbers. And the one thing a computer's not good at is being random. It's incredibly deterministic. So there are all these terribly interesting algorithms about how you produce pseudo-random numbers. But one of the things you can do with quantum computing is you can produce what appear to be truly random numbers. Because you don't know, you can cause something to fall out of superposition into a truly random configuration. And there's a lot of people working on kind of a subset of quantum computing, which is quantum devices to produce random numbers. And that might actually be where people in the not too distant future, if you're talking 2025, you might see it by 2025, things appearing in general purpose computing, a specialized bit of hardware that's based on some sort of quantum effect. Oh, my clock's going off. Some sort of quantum effect that helps produce random numbers to support the cryptography that we use today. So that's a really good point, actually.
We have another one from Peter Hollifield. He's very interested. What computer did you learn to program on? He says a PDP 7/8.
Yes. A PDP 8 was my first, with toggles, purple toggles on the front. Yes. And we had the huge investment that the organization I worked with at the time made was in what's called an FPS 120B array processor, which sat next to it and attached to it. And that was for doing floating point arithmetic, because we were actually trying to do digital signal processing and fast Fourier transforms. So we were actually producing digital DFTs and FFTs. That was what we were doing with it.
Wow. We have some more questions. Jonathan Parker, he comments, this is about the Ghost protocol. What would stop a conversation taking place between parties of just encrypted text? It would be a slow conversation, so the ghost may be able to sit in the conversation, but all they would see is ciphertext between the two parties. It sounds like a wasted effort at that point to implement something like this. They would catch the idiots, would struggle to catch the real criminals.
No, I probably didn't explain it very well. The idea of the Ghost protocol is not just being able to eavesdrop, but you get the keys. In end-to-end encryption, in fact, most of it uses Diffie-Hellman of one sort or another to exchange. So Bill and I are having a conversation. We will exchange our key so that we've then got the shared secret using, say, Diffie-Hellman, and we will revert to AES. But in that process, if you're a ghost, think about how group chats work in something like WhatsApp. They are still end-to-end encrypted, so everybody has that shared secret. But the third person in the conversation, in this case, the ghost, would simply be given the shared secret. So they would be able to see the ciphertext. It would be, they could convert it into plain text. That's the whole point about the Ghost protocol. It's just you wouldn't see them in the conversation.
Peter Hollifield also asked another question. He says, have you seen enough evidence to validate the recent announcement from a private company that claims to have a method to threaten symmetric encryption?
Really? Which one? I haven't seen that.
He doesn't say. He says a recent announcement from a private company. So he doesn't say. I'm not familiar with that.
I want to know now. I've seen nothing that threatens symmetric encryption. In fact, one of the things about quantum computing is that it's the way it would attack symmetric encryption is by effectively brute forcing, guessing that shared secret, that key that you exchange. And all you effectively need to do is double the length of the key, and you cause it to become exponentially harder, even for, there's a thing called Grover's algorithm, which is a fast quantum search algorithm, but it doesn't increase the efficiency exponentially like Shor's algorithm does. It only does it quadratically. So you just need to double the key length. So, but I've not seen, unless somebody has found, I mean, there's so many different types of symmetric encryption out there as well. Be interested to know which ones they think they've found a problem with, or a method of cracking it. There are lots of companies out there with devices, which, for example, there's a company called Grey Key, and there's another one, I forgot the name of an Israeli company, which claims to be able to crack your iPhones and things. All of them are not, or rather none of them are actually breaking the encryption. It's like there are methods out there of reading signal messages, but which is encrypted, but they're not breaking the encryption. What they're effectively doing is it's side channel attacks. They're breaking into your phone in some way, or they're breaking into your PC in some way, and reading it in that. It's equipment interference, if you remember that concept I talked about earlier, where they're able to read it outside the encrypted channel. So maybe that's what he's referring to, or she's referring to. But I'd be interested.
I think one of the challenges, and you're absolutely right. I think that it's not the thrust of what's happening right now is not necessarily to try and crack the encryption, because it's mathematically and technically very, very difficult. I think where they are putting their much more of their focus, especially the nation states, and if you read some of the reports coming out, is they're focusing on the individual. It's the weakness of the employee, actually, the human element in all of this, that's the weak point. And that being able to exploit this is kind of the key.
If you look at cybersecurity in general, which I tend to work across, 95% of all data breaches, there's a human element. It's the picnic problem. It's the problem in the chair, not in the computer. And it's, if you think about, I mean, I wrote an article, go look it up on the BBC, called The 7 Deadly Sins That Hackers Use. It's all social engineering, and it's still the most effective way of getting in. So why give yourself a headache trying to break the encryption? It's just not worth it, when actually you can convince someone to give it the best one ever. Is still the one that we used to use in my misguided early career, when you wanted to break into an organization and you needed somebody's username and password. The most valuable piece of information was the internal telephone directory, because all you would do was phone around the various extensions and say, "Hi, I'm from IT support about the problem you reported." The first 99 people say I didn't report a problem. The 100th person say, "Oh yeah, thanks for phoning back." And you say, "Just give me your username and password. I can't get it just at the moment, and then I'll solve your problem for you." And they'll give it to you. So getting people to give things away is so much easier than trying to crack the encryption in the first place, or even guess the password.
Absolutely. Bill said we'll run for about another 10 minutes.
Oh yeah, I'm easy. Whatever. Yeah.
So
students probably want better things to do on Friday night, students.
Any other questions? Do we have any other questions? I mean, I don't want to kind of monopolize the conversation here, but it's fascinating. This is a really fascinating subject.
Is it okay to ask a question?
Yeah, absolutely. Fire away.
Sure, thanks. Slightly off topic of the more academic, but I alluded to it with the question about the computer programming, what you learnt on, but really fascinating to learn that you personally probably knew or acquainted with or have stories to tell of early days of computing and things like that. I just wonder if there's any of those things that if we have a spare minute and there's no other questions, it'll be fascinating to hear some of that sort of stuff from the
I mean, I think there are some skills that are actually being lost a little bit in modern computing when it's taught, because as I said, when you go back and actually look at some of the processes that again, I wouldn't wish something like assembler on my worst enemy, because trying to write in those sort of languages were just awful. And even writing, something like C or C++, oh God, it's just the number of mistakes you can make in there. It's not friendly at all. So, when I got to things like Fortran, or nowadays writing in C#, it's like, it's a blessed release. But having said that, there are some skills like limited resources. If you don't have that much memory or that much disk space, and I'm not joking, 40 megabyte disks we had, which were, they big and on multiple platters, which cost £10,000 each. You had to make sure that every megabyte was used properly. So I do notice these days that, mostly because of the security side of things, there's a lot of, I guess I'd call it bloatware. There's a lot of code left in things that has no function anymore, and yet has problems with it. So that it's quite an interesting skill. Optimization and running things, it's kind of coming back. One of the things that's starting to happen is because of IoT and people again trying to get more and more things. Take crypto, for example, trying to get crypto to run on some of the IoT devices. And looking for lightweight solutions that will run on the much smaller processors rather than the great big hefty thing I've got sat in front of me. If I'm trying to run on one of the little pieces I've got over here, which I'm building, you think to yourself, actually those skills, they may have been forgotten, but they're actually still needed. So I suppose that's one of the things. Now you can do so much more with the computing, but in some ways you're kind of abstracted from a lot of what's there. So it's quite good to know how things are put together. Some of the simple principles, like I was just trying to think when I was talking to the students the other day about, it's a bit like driving a modern car. When I first started to drive, you had to know how to tune carburetors and what a feeler gauge was, and how to take the head off and all that sort of stuff. Get a youngster driving a car, they don't know what's under the bonnet. It's all just sealed boxes. And unfortunately, a lot of computing is taught these days in that way, in that it's about how to use it and what you can use it for rather than how it works. I must admit, this is a personal bias, but I'm more fascinated by how it works rather than. I also like what I can do with it, but and that's one of the reasons I got into security, to be honest, because I like taking things apart to find out how they work. But it's a bit like trying to take a modern laptop apart. You do it at your peril because, not only are there always screws left over when you put it back together again, but nothing ever works because, it's not meant to be taken apart. Things are not meant to be repaired. Whereas when I think of the number of boards and, wires, plug boards, things we used to have out on the floor, 30, 40 years ago, that's what worries me a little bit, that some of that much more hands-on side of things, it's good for people to see that and understand some of the principles behind it.
Just to reinforce that, IoT now, as you said, constraint environments, TinyML is becoming, really quite an interesting field, because you can then start to do machine learning on very, very small boards. And one of the other things that I can remember back in the day, talking about programmers using constrained environments, the stories that came out, Russian programmers apparently were the best in the world in their day, because the Americans used to restrict the amount of physical hardware and the processing capabilities that the Russians could get hold of. So it was all homegrown stuff, very, very, whatever they could find, they would use. And it was usually through, industrial intelligence. And they would only be able to get the very much older designs for all of their stuff. And the Americans would be used to much, much greater kind of capacities and storage. And they would develop all of this kind of bloatware, which seems to be, and the Russians, they would have these much smaller memory constraints, and their code would be very, very tight. And in fact, as legend, the Russians developed the very first viruses as a means of copyright protection.
Yes.
And it's fascinating. The histories of all of this is absolutely fascinating.
One of the things that going way back with the old adversaries in the Soviet Union. One of the problems they had was, we could be very lazy, because actually most high-level languages, as they started to develop, were based on English, whereas of course they all wrote in Cyrillic. So actually it was quite difficult for them to do it. So in some ways they kind of understood it more, and they were a lot more efficient about even how they used the language. And you could see that even when you did manage to get hold of things and decompile them or reverse engineer them, just some of the comments, things like that. But it's fascinating now when you reverse things and you find the amount of orphan code that's still in there. And of course, as I said, that's a huge security risk. And what is quite interesting, that it's not 10 years ago, it's nearly 20 years ago now, with Microsoft's trusted computing initiative, one of the big initiatives they had was to go through and identify redundant code, because there's 10 million lines in Windows 10, but actually how much of it is actually used. And it turned out, it's different in Windows 10 now because it was written from the ground upwards, but this was when they were back in sort of Windows Vista and things like that, and Windows XP. They found that actually there was so much they could rip out of the thing, not leave all these buffer overflows and goodness only knows what in there. And it didn't affect the price of fish at all.
We've got one last question again from Peter Hollyfield. He says, talking of tight code, are you involved in the topic of mathematically proven code as a security mitigation?
Actually, I'm not, but a couple of my colleagues at Surrey are. In fact, they have a formal method. In fact, we've just started a new group, which I've joined to try and learn things, because I'm not a formal methods person at all. My maths is appalling. It's like my programming. It's just appalling. But the formal methods group, and it's quite interesting going back to the days when we used to build things in certain organizations in government. They preferred certain languages like Ada, because they weren't proven, but you could formally prove different functions in them. And there's actually quite a move now to with formal methods to try and move into what's called software development factories, where you can, in some ways, you've kind of got chunks of proven code and you can reuse those and sort of build proof upon proof of trustworthiness. And it's as I say, I'm still learning, and it's an absolutely fascinating area. But yeah, the mathematical proofs are emerging as to how all of that happens. But it's one of those things where it's only, I'm a dreadful intellectual butterfly, and there's only so many hours in the day. But I kind of want to go off and learn about that now.
Fantastic. So we've reached the end of this fantastic conversation with you. Really want to thank Bill as well for inviting you on. It's always a pleasure to meet you, Alan. I mean, you are a fountain of knowledge, and it's a shame that we can't host this because, you know, the last time that we met actually was at Napier, and it would be fantastic to host you again at some point in the future.
Anytime. Yeah.
So thank you very, very much, and for the opportunity to ask you all of these fantastic questions, and I look forward to you again. So thank you very much indeed.
Pleasure. I've not had a Zoom clap or a Team clap before. That's very good. Thank you very much. It's a pleasure as always. I'm sure we'll get to talk again soon.
Thank you for that. And we've recorded the session, so if there's anything that you don't want us to publish anywhere, then just say that. Thank you so much, Alan. It was really enlightening.
And if the students have any, I mean, my email's well known, so if anybody has any questions, then just bung us an email.
That's great. Okay, thank you to everybody, and thank you for staying on. So many of you. That's amazing on a Friday evening. Go and have some wine, some whiskey, or non-alcoholic drinks.
That's all the encouragement I need.
Thank you so much.
Thank you very much, Alan.
Thank you. Bye-bye.
Thank you.
Thank you.
Thank you. Bye.
Bye-bye.
Bye. Bye.